The prediction of DBPs, what it means is like we know that the DBPs are the harmful chemicals that are formed when chlorine reacts with natural organic matter under certain environmental conditions. So we try to examine those environmental conditions using our sensing systems and then build a machine learning models to predict the reaction and see how the concentrations of these DBPs are formed in the drinking water distribution system. That's how the prediction system is where we are defining it.
What kind of data feeds into these algorithms?
The type of data that we feed into these prediction algorithms is like 5 of the water quality parameters like temperature, pH, conductivity, oxidation reduction potential, and also the dissolved oxygen. And we are also concentrating on like 6 of the optical parameters, somewhere like 255 nanometer transmission, 280, 400, and also the RGB transmissions. So these 11 parameters are the major input data for this prediction algorithms.
Where DBPs are likely to form.
Using the prediction algorithm, we can try to understand in the entire water distribution system where the hotspots for this DBPs formation is higher, and also we can see the risky zones where the DBPs are formed. So installing those sensors at that particular locations in the hotspots will be more helpful.
What challenges do you face when trying to simulate a real, often unpredictable water system?
The type of NOM is the reason for what kind of a DBP is being produced. To understand that and to simulate that in real time, every location has different types of NOMs, which is unpredictable at that point of time. So this will be a major challenge when we are designing the predicting systems.
Can the model learn and improve as new information comes in?
Yes, with the new information, the model can be improved and it can learn understanding the DBPs. This is possible. Could you tell us about the optical sensors you're developing for DBP detection?
So together with the water quality parameters that we are monitoring, we also use an optical sensor, and this optical sensor is measuring 6 different wavelengths. And what we do is we measure the absorbance of light by the water, and this actually tells something about the chemical composition. This is an indirect way of determining the water quality parameters during the experiment. So the optical sensors, together with the water quality parameter sensors, they give an impression of what the environmental parameters are, the conditions at which these DBPs are forming. And because we have this information, we can say something about how these DBPs are forming and how fast they are forming and at what level. So we get an indirect measurement by combining the information of all these sensors. So the individual parameters don't say directly something about the DBPs, but they say something, for instance, about the turbidity, so how cloudy it is. It can also say something about the concentration of NOM, it can say something about the concentration of chlorine, and all of these parameters are important for the prediction.
Could they eventually be used not just by big utilities, but in smaller community systems too?
So the nice thing about these sensor systems is actually that they're relatively cheap. So that means that not only the bigger companies can use them, but also smaller community systems, they can be applied.
To test the center knowledge base, 3 of the sensor sets are deployed in the pilot location, Coimbra, Portugal. So the data that is collected about the water quality from these 3 locations is transferred every 1 hour to the center knowledge base. There we have this opportunity to visualize the graphical representation of the data, and we are also able to download the data whenever we need it.
In the coming 10 years with the sensors, we can actually predict and monitor the DBP concentrations. So this means that we have a much better understanding of how these DBPs are formed, where they are formed, and it also means that we can take action. And it's very convenient if all that information is coming together at a single location, because this actually helps to take action in a proper way.
Could this integrated approach be adapted to tackle other water contaminants beyond DBPs?
So combining data of several simple sensors and then making models to predict something that you don't measure directly has actually already been applied in several projects. And it is proven that, for instance, in groundwater, we could predict the concentration of hydrocarbons. But you can also think of applying this in wastewater treatment systems, where you can actually monitor the complete wastewater treatment facility.
What is the next steps to take these innovations from pilot scale to widespread?
So during this project, we learned at pilot locations how we could link the formation of DBPs to the parameters that we are measuring with the monitoring sets. But this is only at a single location, and if you want to also apply the same technique at other locations, you probably need to learn more about those systems as well. So what we are currently doing is, in the laboratory, we are testing at different circumstances and also with different types of natural organic matter to create a data set that we could use for training. And it has to make it easier for us to also apply these techniques at different locations.
Who knows about disinfection byproducts? And how are they related to our water quality? Most people don't know much. But did you know that disinfection byproducts are part of your everyday life and can affect your health? You drink them, inhale them, and shower in them every day. We have made huge progress over what foods to avoid, which plastics are safe, but when it comes to what we consume more than anything else, our water, people have no idea about disinfection byproducts and what they can do about them to protect their health.
Disinfection byproducts are chemical substances produced during the treatment of water from organic materials. Think about chlorine added to the swimming pool to keep the water safe. Our drinking water also goes through appropriate treatment processes. Research shows that disinfection byproducts are associated with health risks if they're in high concentration. So if DBPs are inevitable with current treatment methods, the real question then becomes, what can we do about them? Our trustworthy distributed intelligence team here at the University of Leeds is a proud member of the H2OforAll project. We're leading innovative and interdisciplinary research on how to raise awareness and engagement related to disinfection byproducts.
Our focus is empowering the citizen, the end water consumer who drinks the water. Using value-sensitive AI assistants and insights from social science, we aim to mobilize water consumers with simple, cost-effective actions at home that reduce the exposure to disinfection byproducts and improve water quality.
To achieve this ambitious goal, we discovered and profiled residential actions that influence water quality. So think boiling, flushing taps, changing pipes, ventilation, and so on. We also explored how easy for water consumers is to adopt these actions by analysing the cost, time, and frequency required to apply them. This allowed us to build smart recommendations for different types of people. Busy and cost sensitive, ventilating between showers may be ideal. You're willing to invest? A distillation unit could be a better option here.
Using these insights, we progress further to understand which factors are important for people to adopt residential actions that protect water quality. Are there any trade-offs that people make between water quality protection, cost, and practicality of the actions? And beyond this, do people trust water companies? Do they feel responsible? Do they even want to take action for protecting water quality? Based on a large-scale study across Europe with more than 3,000 participants, we found something remarkable. Water consumers choose impactful products with which they demonstrated they can improve their water quality. And this based on an overall higher awareness they build up about disinfection byproducts and how they are involved in their everyday life. And in doing so, we were also able to learn about purchasing habits.
Are you interested yourself to learn more about disinfection byproducts and know how to engage with water quality protection? Try our innovative gamified web platform here. You will receive practical recommendations tailored to your own priorities and constraints at home. You will be able to monitor your progress and improve your actions further as you build awareness about disinfection byproducts.
This research demonstrates a groundbreaking win-win synergy between water suppliers joining forces with citizens for the promotion and protection of water quality. These results will inform future policy on water safety. They constitute a new blueprint of reapproaching water quality with active citizens' engagement.